Welcome to our explainer. Today, we're going to tackle a couple of big mysteries in the world of large language models. First up, why does your super fast model sometimes feel, well, kind of slow? And second, we're going to get to the bottom of what on earth sparsity actually means.
So let's kick things off with a feeling I'm sure you've had. You're working with this state-of-the-art AI, right? The benchmarks are screaming fast, promising amazing tokens per second, but then you feed it a really long prompt and you're just sitting there waiting for that first word to appear. What is going on?
Okay, so the answer to that mystery actually lies in something a lot of people miss. See, an LLM doesn't just have one speed. It actually operates at two totally different speeds, and understanding them is key.
So on one hand, you've got the prompt eval rate. You can think of this as how fast the model reads and understands your question. And on the other hand, you have the output tokens per second. That's its writing speed, how fast it spits out the answer. These are two totally separate steps.
Let's look at that prompt evaluation part first. This happens just once, right at the beginning. The model literally has to ingest and process every single token in your prompt before it can generate a single word in response. And here's the kicker. The longer your prompt, the longer that initial wait is going to be. It doesn't matter how fast the model can write later on. This first step can be a real bottleneck.
So once the model has finished thinking about your prompt, then it starts generating the response. This is the part we all see, the words streaming onto the screen. It's the speed that gets all the attention in marketing, you know? But as we're seeing, it's really only half the picture.
And this right here puts it all together perfectly. Your total wait time, what we call latency, is just a simple addition problem. It's the time to first token plus the generation time. And boom, mystery number one is solved. That's why a model with a killer generation speed can still feel slow if its prompt evaluation rate can't keep up with your long inputs.
So naturally, this whole speed problem has everyone searching for ways to make these models more efficient. And that quest leads us directly to a really powerful, but let's be honest, a really confusing idea: sparse models.
So what is a sparse model anyway? Well, the core idea is actually pretty intuitive. Instead of firing up the entire gigantic brain of the model for every single little thing, a sparse model only uses a small fraction of its brain. Just the parts it needs for that specific input. It's like you don't use every muscle in your body to pick up a pencil, right? Same idea.
And this is where our second mystery really kicks into high gear. Because whenever you hear the word sparse, another term almost always pops up right alongside it: mixture of experts, or MOE. So, what is the deal? What's the connection here?
Okay, so an MOE model is basically like having a committee of specialists. You've got all these different mini models called experts, and then you have a router. The router's job is to look at each piece of incoming data and say, okay, you're a math problem. You go to the math expert. You're about poetry. You go to the literature expert. This table really helps clear things up. Are MOE models sparse? Yep, absolutely. By definition, they only use a few experts at a time. But, and this is the important part, are all sparse models MOEs? Nope, not at all. MOE is just one way to achieve sparsity.
I love this quote because it just says it all perfectly. Sparsity is the outcome we want, using only a part of the model. MO is just one method for getting that outcome. It's a how, not a what. There are other ways to do it that don't involve a mixture of experts at all.
All right, now we get to the real reason this is all so confusing. The absolute heart of the mystery. It turns out the entire community, for historical reasons, uses the exact same word, sparse, to mean two completely, fundamentally different things.
Okay, look at this quote. It sounds totally contradictory, right? A sparse MOE model isn't sparse? How does that work? Well, believe it or not, this statement is 100% true. And it gets right to the heart of all the confusion, especially for the engineers who actually have to build these things.
Okay, here it is, the two meanings side by side. On one side, you have weight sparsity. This is what an engineer usually thinks of. Lots of the numbers in the model's brain are literally zeros. This makes the model physically smaller in memory. Then you have compute sparsity. In this case, all the numbers are there, they're all non-zero, taking up space, but for any given task, you only use a fraction of them. MO models fall squarely into this second category. They are compute sparse.
So if your brain is hurting a little bit right now and you're thinking, wait, using the same word for two different concepts is kind of stupid, well,
you are not wrong. It is stupid. It's just one of those historical accidents in terminology that we're all stuck with now. This chart is your perfect guide to keeping this straight. A normal, dense model, not sparse in either way. A pruned model, where you've literally zeroed out connections, that's weight sparse. But an MOE model, it's not weight sparse. All the experts are fully loaded in memory. It's compute sparse because it only uses a few of them at a time.
And here's the absolute worst part. This is what makes the term so actively misleading. When an engineer hears sparse, they think less memory, smaller model. But a sparse MOE model does the opposite. It actually increases your memory footprint because you have to load all those experts into VWAM. The name literally suggests the reverse of what it does to your system resources. It's wild.
Okay, so there's one last piece to this puzzle. If that router is just picking experts, how does it get any better? How does it learn which expert is the right one to pick?
This brings us to a really core technical question. You see, for these models to learn, the math has to be differentiable. Basically, it needs to be smooth so you can calculate how to make tiny improvements. But the act of choosing expert A over expert B, well, that's not a smooth decision. It's a hard choice. So how does it learn?
And the answer is, it doesn't. Not directly anyway. That selection step isn't differentiable. So engineers came up with this really clever training hack. The router assigns a probability score to each expert. Then it makes a hard choice and picks the top one or two. The magic is that the feedback for learning only goes back through the experts that actually got picked. It's a neat workaround. But that's not the whole story. To help the router learn better, they add another clever piece to the training puzzle, something called a load balancing loss. This is basically an extra rule that punishes the router if it sends all the work to just one or two favorite experts. It encourages it to spread the love and use all the experts evenly, which makes the whole system learn much more effectively.
All right, let's wrap this all up. What did we learn? First, LLMs have two speeds, prompt processing and token generation, and both matter. Second, the word sparse is a trap. It can mean weight sparse, which saves memory, or compute sparse, which saves calculations but often uses more memory. MOE models are compute sparse. And finally, they learn how to route tokens using some really clever training tricks.
You know, this whole thing is a perfect example of how the language we use in AI can get super confusing, especially when different fields collide. It really makes you think, doesn't it? What other stupid words are out there in AI that are tripping us all up? Thanks for joining this explainer.